let's have a look at multiple input and output channels when we do this in Python. So let's recall what we have. So we have multiple input channels. You convolve it with some kernel. So you basically go over the input. In this case, it's a 2x2 applied to a 3x3 image. And so we get this output here. Okay. So in order to get started, well, we need to import MXNet. And I'm going to define a correlation multi-in. And all I'm doing is I'm just taking the standard correlation function. And now I'm going to use this to apply it to multiple input channels. And then in the end, I just add it up. This is maybe not the most elegant way to do it, but this just illustrates the point. So then, well, let's have a look at what happens if we apply this to some data. So this is exactly the example from before. I take two 3x3 channels, right? I apply a 2x2 kernel. Again, I need to have a kernel for each channel. I add this all up, and lo and behold, I get exactly the numbers that we saw before on the slides. Okay, so now if I want to have multiple output channels, well, what I simply do is I apply the multiple input channel setting for each of the output channels, and this gives me a multi-input, multi-output channel. Okay, so for that, now I need to get a kernel which has multiple output channels. I'm going to make my life easy. I'm just going to take the convolutional kernel K. I'm going to add 1 to it, and I'm going to add 2 to it. I'm going to stack it up. So this gives me a 3x2x2x2 tensor. So it's 2x2 for the 2D for the 2x2 convolutions. It's another 2 here for the 2 input dimensions, and it's 3 for the 3 output dimensions. Okay. So now let's see what happens when we apply this. So this applies the kernel to a 2-channel output inputs for a 3x3 image, and we get out of it 3 2x2 matrices. So it's basically a 3x2x2 tensor. That's exactly what we engineered. Now let's look at 1x1 convolutions, and I'm going to define an alternative definition for 1x1 convolutions. I'm going to extract bias and all the other terms from X, right? Get the corresponding output channels, and now I'm going to reshape X to allow me to perform matrix vector multiply. It's just the number of input dimensions. Then I do the same thing for, this is my kernel. It's now becomes a 2x2 matrix, or, it's a matrix with output and input dimensions. And I perform a matrix vector multiply. And in the end, I reshape it, and here's what we get. Mind you, I skipped the bias just because otherwise the code looks a little bit lazy. So there we go. Now let's actually compare what happens if I do this and compare it to 1x1 convolutions applied the traditional way. So remember, this is my 1x1 convolutional kernel with 2 input and 3 output dimensions. And the image, it's 2 output and 3 input dimensions. The image itself is a 3x3 image with 3 channels. In that case, I can compute the output once by using multi-in, multi-out, and the other case by using the 1x1 version. And lo and behold, I get exactly the same result, which is to be expected because that's what I engineered. This is just to illustrate the point that 1x1 convolutions are effectively multi-layer perceptrons applied on a per pixel basis. And this allows me to perform additional nonlinear transforms based on the channels. So for instance, if I wanted to find out whether I have a horizontal and a vertical edge I would take the horizontal edge channel, the vertical edge channel, and then combine these appropriately to get another new feature out of it. And I could do this on a pixel level. So this concludes this conversation about input and output channels.